Welcome! In this session, we'll dive into LeetCode problem number 1296, divide array in sets of k consecutive numbers. The goal is to determine if a given array can be grouped into sets of exactly k consecutive integers. This problem challenges our understanding of sorting and hash maps, so let's explore its solution and key insights together. In this problem, you're given an integer array called nums and a positive integer k. The objective is to determine if it's possible to divide the array into sets of k consecutive numbers. Each set must have exactly k numbers, and no number can appear in more than one set. Essentially, you're trying to partition the array so that every set has numbers in a strictly consecutive sequence of size k. If this is achievable, the function should return true, otherwise, it should return false. The input format specifies that nums is an array of length n where n can be as large as 100,000 and each number in the array falls between 1 and 1 billion. The value of k is also a positive integer, ranging from 1 to the length of the array. The output will simply be a Boolean value, true or false, depending on whether the partitioning is possible. Let's look at an example to understand this better. Suppose nums is the array 1 2 3 3 4 4 5 6 and k is 4. The output in this case would be true. Here's why: we can divide the array into two sets. The first set is 1 2 3 4, which contains 4 consecutive numbers, and the second set is 3 4 5 6, which also contains 4 consecutive numbers. Notice that all the numbers in the array are used, and no number appears in more than one set. This satisfies the conditions of the problem, so the result is true. Now consider another example where nums is 3 3 2 2 1 1 and k is 3. The output for this case is also true. Here, we can divide the array into two sets, 1 2 3 and 1 2 3. Both sets contain exactly 3 consecutive numbers, and all numbers in the array are used without any overlap between the sets. This means the array can be successfully partitioned, so the result is true. However, let's examine a different situation where nums is 1 2 3 4 and k is 3. In this case, the output is false. Although the array contains consecutive numbers, it's not possible to divide it into sets of size 3. For example, if we try to form the set 1 2 3, the number 4 is left over and cannot form a valid set of 3 consecutive numbers. Since we cannot use all the numbers in the array to create sets of size k, the result is false. To solve this problem, we must carefully ensure that the array can be divided into sets of exactly k consecutive numbers, with no leftover elements. There are also some important edge cases to consider. First, if k is 1, then any array will return true because each number can form its own set. Second, if the length of the array is not divisible by k, we can immediately return false, since it's impossible to divide the array into equal-sized sets. Third, if all the numbers in the array are the same, the result will be false unless k is 1, because consecutive numbers cannot be formed in this scenario. Finally, we need to handle very large arrays efficiently, as the length of nums can go up to 100,000. This means our solution must be optimized to meet time complexity requirements. To solve the problem of dividing an array into sets of k consecutive numbers, we explored several approaches. The first is the brute force method. The intuition here is to repeatedly generate subsets of size k and check if each subset contains consecutive numbers. To implement this, we would sort the array, find the smallest number, and try to construct a group of k consecutive numbers one by one, removing those numbers from the array as we go. While this approach is straightforward, its complexity is a major drawback. Sorting the array takes n log n, but repeatedly searching for and removing k elements makes the overall time complexity approximately n squared. This inefficiency becomes a significant issue for larger arrays, as the repeated scanning and modification of the array are computationally expensive. The second approach we considered is an optimized method using a hash map. Here, the problem is reframed into organizing the array's numbers based on their frequencies. By starting with the smallest number and attempting to form a group of k consecutive numbers, we can manage this efficiently using a frequency map to track how many times each number appears. This avoids unnecessary operations and ensures that if a number cannot form part of a valid group, we can immediately conclude that the division is impossible. In the hash map approach, the first step is to count the frequency of each number in the array. Once we have this frequency map, we sort the keys of the map and iterate through them. For each number, if its frequency is greater than 0, we attempt to form a group of k consecutive numbers starting from that number. As we build the group, we reduce the frequencies of the numbers involved. If at any point a group cannot be formed, meaning a required number is missing or its frequency is insufficient, we return false. The time complexity of this approach is efficient. Sorting the array takes O, n log n, and iterating through the numbers while adjusting frequencies only adds an O, n, cost, resulting in an overall complexity of O, n log n. The advantage of this method is that it avoids redundant operations, making it both elegant and practical. Another approach we considered is the greedy method using a priority queue, or a min heap. The intuition here is similar: always process the smallest available number first to ensure groups are formed in order. By using heap operations for inserting and removing numbers, this approach also achieves a time complexity of O, n log n. However, the heap-based solution introduces additional complexity in implementation, as managing the heap adds overhead compared to the simplicity of a hash map. Ultimately, we chose the optimized approach using a hash map as the best solution for this problem. This method strikes an excellent balance between efficiency, simplicity, and clarity of implementation. The frequency map provides a direct way to track the availability of numbers, and sorting ensures that groups are formed in the correct order. Unlike the brute force approach, it eliminates unnecessary overhead, and compared to the heap-based solution, it is easier to implement without sacrificing performance. However, there are trade-offs to consider. While this approach is efficient, it does require additional space to store the frequency map, leading to a space complexity of O, n. The heap-based method remains a valid alternative but does not offer a significant performance advantage to justify its added complexity. The key insight that made this approach effective was the realization that forming consecutive groups is equivalent to simply checking the availability of numbers in order. By starting with the smallest number and reducing frequencies as we form groups, we ensure correctness while avoiding redundant checks. This clarity and efficiency make the hash map approach an ideal choice for solving this problem. In this problem, we are tasked with determining whether it is possible to divide the given array, nums, into groups of exactly k consecutive numbers. Each number must be used exactly once, and the array can include duplicates. To solve this efficiently, we will use a greedy approach combined with a frequency map, which tracks the count of each number, and a min heap to ensure we process numbers in ascending order. Let's break the process into steps. First, we start with input validation. If the length of the array is not divisible by k, it is immediately impossible to divide the array into groups of size k, so we return false. Next, we build a frequency map, which counts how many times each number appears in nums. For example, if nums is 1 2 3 3 4 4 5 6, the frequency map would look like this: 1 1 2 1 3 2 4 2 5 1 6 1. This map will be the foundation for forming our groups. Now, once we have the frequency map, the next step is to process the numbers in ascending order. To achieve this, we extract the keys from the frequency map and sort them. This ensures that we always work with the smallest available number first, which is crucial for forming consecutive groups. For the earlier example, the sorted keys would be 1 2 3 4 5 6. With the keys sorted, we move on to the core of the algorithm, greedy group formation. For each number in the sorted keys, we check its frequency. If the frequency is greater than 0, we attempt to form a group starting from that number. For a group starting at number, we decrement the frequency of number and the next k1 consecutive numbers, such as number plus 1, number plus 2, and so on, by the same amount. If at any point a number needed for the group does not exist in the frequency map or its frequency is insufficient, we know the group cannot be formed, and we return false. If we successfully form groups for all numbers, we return true. Additionally, this approach naturally handles edge cases, such as leftover numbers in the frequency map or when grouping is impossible due to gaps in the sequence. Let's walk through an example to see the algorithm in action. Suppose nums is 1 2 3 3 4 4 5 6 and k is 4. First, we build the frequency map 1 1 2 1 3 2 4 2 5 1 6 1. Then, we sort the keys, resulting in 1 2 3 4 5 6. Starting at 1, we form the group 1, 2, 3, 4 by decrementing the frequencies of 1, 2, 3, and 4 by 1. The updated frequency map becomes 3, 1, 4, 1, 5, 1, 6, 1. Next, we move to 3, which still has a frequency of 1. We form the group 3, 4, 5, 6, decrementing the frequencies of 3, 4, 5, and 6 by 1. The frequency map is now empty, indicating that all numbers have been successfully grouped. Therefore, we return true. This example highlights the efficiency of using a frequency map and sorting the keys. The two main data structures here are the frequency map, which provides constant time access and updates, and the sorted keys or min-heap, which ensures the numbers are processed in ascending order. Let's analyze the complexity of our solution. First, constructing the frequency map requires a single pass through the array, resulting in a time complexity of O(n). Sorting the keys takes O(n) log n, as it depends on the size of the input array. The group formation step involves iterating through the sorted keys and processing each number, which takes O(n*k) in the worst case. Combining these, the overall time complexity is O(n) log n. For space complexity, the frequency map and sorted keys each require O(n) space, resulting in a total space complexity of O(n). Key insights from this approach include the importance of sorting the keys to process numbers in the correct order, using the frequency map for efficient tracking of available numbers, and adopting a greedy strategy to form groups as early as possible. This ensures that any potential issues, such as gaps in the sequence or insufficient frequencies, are caught immediately. The algorithm also naturally handles edge cases, such as when k is larger than the array length or when grouping is impossible due to gaps in the sequence, by validating inputs and checking the frequency map during group formation. Here, we start by importing the necessary modules counter from the collections library to count the frequency of elements, and heap4 working with a min-heap. Inside the isPossibleDivide function, the first check ensures that the total number of elements in the array is divisible by k. If not, we immediately return false since it's impossible to divide the array into groups of k consecutive numbers. Next, we use counter to calculate the frequency of each number in the array and store these frequencies in a dictionary-like structure. To process the numbers in sorted order, we convert the keys of this frequency dictionary into a list and use Heapify to transform it into a min-heap. This allows us to efficiently retrieve the smallest number as we form groups. Then, we enter a loop that continues until the heap is empty. The variable start is initialized to the smallest number currently in the heap, which will serve as the starting point of the next group of k consecutive numbers. For each number in the range from start to start plus k, we check if the number exists in the frequency dictionary. If it doesn't, we return false because a complete group cannot be formed. If it does exist, we decrement its frequency by 1, indicating that this number has been used. If the frequency of a number becomes 0, we need to remove it from the heap. However, if the number does not match the smallest element in the heap, we return false because the sequence is broken. Finally, if all groups are successfully formed and the heap is emptied without issues, we return true, indicating that it is possible to divide the array into the required sets of k consecutive numbers. Here, we start by defining the isPossibleDivide method, which takes an array of integers nums and an integer k. The goal is to determine if it's possible to divide the array into sets of k consecutive numbers. The first check ensures that the length of the array is divisible by k. If it's not, the method immediately returns false because forming groups of k consecutive numbers would be impossible in this case. Next, we calculate the frequency of each number in the array using a hash map. This map will store each unique number as a key and its count as the value. We then initialize a priority queue, or min-heap, to process the keys in sorted order. This is important because consecutive groups need to be formed starting from the smallest available number. The while loop begins processing as long as the min-heap is not empty. The peek method retrieves the smallest number in the heap, which will serve as the starting point for forming a group of k consecutive numbers. The for loop then attempts to construct this group by iterating through the next k numbers, starting from start. For each number, we check if it exists in the frequency map. If it doesn't, it means we can't form a consecutive group, so the method returns false. If the number exists, we decrement its count in the frequency map. If the count for a number becomes 0, it will be handled in the next section of the code. If the count of a number becomes 0, we need to ensure it is removed from the min heap. However, we also check if the current number we are processing is the smallest in the heap using minHeap.peak. If it's not, it indicates a discrepancy in the order of numbers, and we return false. Otherwise, we remove the number from the heap using poll, ensuring the heap remains updated with only the numbers that still have a non-zero frequency. Once the for loop completes successfully for a group of k consecutive numbers, we continue processing the next smallest number in the heap, repeating the process until the heap is empty. If we manage to process all numbers without encountering any issues, the method returns true, indicating that it is indeed possible to divide the array into sets of k consecutive numbers. This implementation leverages both the hash map for frequency tracking and the priority queue for ordered processing, ensuring correctness and efficiency. To solve this problem, the first step is to check if the length of the array is divisible by k. For the given example, nums has a length of 8, and since 8 is divisible by 4, we can proceed. If it wasn't divisible, it would be impossible to split the array into consecutive groups of size k, and we would return false immediately. Next, we calculate the frequency of each number in the array using a counter. This gives us the frequency dictionary 1, 1, 2, 1, 3, 2, 4, 2, 5, 1, 6, 1. After this, we build a min heap from the keys of this frequency dictionary, which results in a heap of 1, 2, 3, 4, 5, 6, sorted in ascending order. Now, we begin processing the heap. Starting with the smallest element, 1, we attempt to form a group of 4 consecutive numbers, 1, 2, 3, and 4. As we add each of these numbers to the group, we decrease their corresponding frequencies in the dictionary. For example, decreasing the frequency of 1 results in frequency 1 becoming 0, and similarly, we adjust the frequencies for 2, 3, and 4. Once the frequency of a number reaches 0, we remove it from the heap. After processing these 4 numbers, 1 and 2 are removed from the heap, leaving us with 3, 4, 5, 6. Now, we continue processing the heap by starting with the next smallest number, which is 3. Using this number, we form another group of 4 consecutive numbers, 3, 4, 5, and 6. For each number in this group, we reduce its frequency in the dictionary and remove it from the heap if its frequency reaches 0. For instance, decreasing the frequency of 3 results in frequency 3 becoming 0, and the same process is followed for 4, 5, and 6. After processing this group, the heap becomes empty because all these numbers have been removed. At this point, we've successfully formed groups of k consecutive numbers, and since the heap is empty, we can conclude that it's possible to divide the array as required. Therefore, we return true. In a second example, where nums is 1, 2, 3, 4, and k is 3, the length of the array is 4, which is not divisible by 3. In this case, we immediately return false because it's impossible to divide the array into groups of size k. For the third example, nums is 1, 2, 3, 4, 5, 6, 7, 8, 9, and k is 3. The length of nums is 9, and since 9 is divisible by 3, we move forward. First, we calculate the frequency of each number in the array, which results in the dictionary 1, 1, 2, 1, 3, 1, 4, 1, 5, 1, 6, 1, 7, 1, 8, 1, 9, 1. Then, we construct a min heap from the keys of this frequency dictionary, giving us 1, 2, 3, 4, 5, 6, 7, 8, 9. Starting with the smallest number, 1, we form a group of 3 consecutive numbers, 1, 2, and 3. For each of these numbers, we decrease their frequency in the dictionary and remove them from the heap once their frequency reaches 0. After processing this group, the heap is reduced to 4, 5, 6, 7, 8, 9. Next, we start with the smallest number remaining in the heap, which is 4, and form another group, 4, 5, and 6. Again, we decrease the frequency of each number in this group and remove them from the heap when their frequency becomes 0. After processing this group, the heap becomes 7, 8, 9. Finally, we process the remaining numbers in the heap, starting with 7. Using this number, we form the last group, 7, 8, and 9. As with the previous groups, we decrease the frequency of each number and remove them from the heap once their frequency is 0. After completing this step, the heap becomes empty, and all numbers in the array have been successfully grouped into sets of k consecutive numbers. Since the heap is empty and all the groups are valid, we return true as the final output. This confirms that nums can be divided into sets of 3 consecutive numbers as required. The time complexity of our solution is determined by 3 main steps. First, we calculate the frequencies of all numbers in the input array using the counter object. Since this involves iterating through the entire array once, the time complexity for this step is O, n, where n represents the total number of elements in the array. Next, we construct a min-heap from the unique keys of the frequency counter. Since there are m unique numbers in the array, the heap construction process using the heapify function takes O, m, time. Finally, we process the numbers in the min-heap. For each unique number, we try to form a group of size k by checking and decrementing the frequencies of k consecutive numbers. This involves iterating k times for each unique number. Additionally, if the frequency of any number becomes 0, we remove it from the heap, which is an O log m operation. In the worst-case scenario, all m unique numbers are processed, resulting in O, m asterisk k, time for the while loop. Combining these steps gives us the overall time spent in the solution. Now, let's combine all the steps to determine the total time complexity. Counting the frequencies takes O, n, building the heap requires O, m, and the while loop processing contributes O, m asterisk k. Since the number of unique numbers, m, is always less than or equal to the total number of elements, n, we can substitute m with n in the dominant term. This simplifies the total time complexity to O, n asterisk k. Shifting our focus to space complexity, the memory usage is primarily determined by the auxiliary data structures. The counter object uses O, m, space to store the frequency of each unique number, while the min-heap also requires O, m, space for the unique numbers. Other variables, such as loop counters, require constant space, O1. Therefore, the overall space complexity is determined by the counter and the heap, which together amount to O, m. Since m is at most n, the space complexity simplifies to O, n. The total space complexity of our solution is dominated by the counter object and the min-heap, both of which require O, m, space. Since m is at most n, the overall space complexity becomes O, n. Let's compare this approach to a naive solution. A brute force method would involve sorting the array, which takes O, n log n, time, and then repeatedly grouping k consecutive numbers. This process would involve iterating through the array multiple times, leading to an overall time complexity of O, n log n plus n asterisk k, in the worst case. In contrast, the optimized approach we've implemented avoids unnecessary iterations by using a heap and a frequency counter to efficiently track and process groups of k consecutive numbers. This makes our approach significantly more efficient for large values of n and k. When analyzing different scenarios, the best and worst cases both involve O, n asterisk k, time. Even if the array is already arranged into valid groups, the solution still processes all numbers using the same algorithm. To mathematically verify the big O complexity, let's break it down further. The while loop processes each unique number once, and for each number, it performs k consecutive checks. This results in O, m asterisk k, operations in the loop. Since m, the number of unique numbers, is at most n, we can substitute m with n to simplify the term to O, n asterisk k. Additional steps, such as frequency counting with time complexity O, n, and heap construction with O, m, are asymptotically smaller than O, n asterisk k, and do not affect the final result. Therefore, the overall time complexity of the solution is confirmed as O, n asterisk k. This mathematical proof aligns with our earlier analysis and highlights the efficiency of this approach compared to less optimized solutions. When tackling this problem, there are several common mistakes to watch out for. First, not sorting the array is a frequent error. Sorting is crucial because it ensures that numbers are processed in the correct order to form consecutive groups. Without sorting, it's easy to miss valid groupings or create invalid ones. Another mistake is ignoring the frequency of numbers. For example, if you have the array 1 1 2 2 3 3 and k equals 3, you'll need 2 sets of 1 2 3. Overlooking frequencies can result in incomplete groupings. Additionally, modifying the frequency map while iterating over it can lead to logical errors or even runtime issues. It's important to decrement values carefully and avoid directly iterating over the map while making changes. Lastly, don't overlook edge cases. For instance, if k equals 1, any array can be divided into sets of size 1, so the answer will always be true. Or, if the length of the array isn't divisible by k, it's impossible to create equal groups. Arrays with duplicate numbers may require forming multiple identical groups, so these scenarios need to be considered as well. Inefficient brute force solutions are another pitfall. These involve repeatedly scanning the array to find and remove groups of k consecutive numbers, leading to a time complexity of n squared, or worse. This approach quickly becomes infeasible for larger inputs. Now, from an interview perspective, this problem is designed to test your understanding of greedy algorithms and frequency maps. A strong solution involves sorting the array, using a frequency map to track counts, and iterating through the numbers to form valid groupings. Recognizing patterns in grouping problems is also key. Many similar problems, like forming pairs or subsets, require sorting and frequency maps as part of their solutions. The optimal approach here achieves n log n by combining sorting with a greedy strategy. Be prepared to explain the trade-offs of your solution, such as why sorting is necessary and how it affects the runtime, and why brute force is suboptimal in comparison to a greedy approach. This problem is closely related to several others that you may encounter on LeetCode. For example, LeetCode 846, Hand of Straights, involves grouping cards into consecutive sequences and has a similar structure. LeetCode 128, Longest Consecutive Sequence, focuses on finding the longest streak of consecutive numbers, which is another variation on handling consecutive elements. LeetCode 350, Intersection of Two Arrays 2, uses frequency counting to solve array intersection problems. Lastly, LeetCode 406, Queue Reconstruction by Height, is a greedy algorithm problem that also involves sorting and grouping, demonstrating the versatility of these techniques. In terms of alternative approaches, brute force is one way to try solving this problem by repeatedly removing groups of k consecutive numbers. While simple conceptually, it's highly inefficient and not practical for larger inputs. A priority queue can also be used, where you repeatedly extract the smallest element to form groups, but this method is less intuitive compared to sorting. The most efficient and interview-friendly approach remains the greedy strategy with sorting and a frequency map. This ensures an n log n time complexity while maintaining clarity and reliability in forming valid groupings. Thanks for joining me. To wrap up, we tackled this problem using a combination of sorting and hash maps to efficiently form groups of k consecutive numbers. Along the way, we discussed time and space complexities and highlighted key programming concepts. If you enjoyed this walkthrough, feel free to like, subscribe, and come back for more coding insights. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!